So we want to look at endemic malaria and climatic variables. And um, this aspect is very, very important because it builds on the existing courses that we have been listening to since we started the school. And but there are certain things I would like us to know. There are certain things I would like us to know because why it is very important for us to ask the question of how do I incorporate climatic variables? How do I incorporate maybe temperature, rainfall, humidity, whatever the case may be, into my model? It's very, very important that some biological foundations should be known. Very, very important. So I will take us through just synoptic background on malaria, then some biological bedrocks, and then move straight into modeling the thermal responses of, of traits. So in the course of the lecture, we'll get to understand what some of these things, what they mean. But taking this particular class on the assumption that some of the backgrounds we need to know about malaria has been taken by my colleagues, and also the model we'll be using has also been explained by Dr. Afix, and Prof has done a lot of justice to making us to understand the relationship between malaria and also climatic variables. And so I will be building on that existing classes or the previous classes. So the first one is malaria. So we know malaria is a life-threatening disease caused by the Plasmodium species, a group of single-cell eukaryotic parasites transmitted through the bites of infectious, blood-seeking female Anopheles mosquitoes. These terms are very, very important. Then, since we are looking at endemic malaria not as an epidemic, that means it's already existing. It has established itself within the particular location of interest. Maybe, for instance, now Nigeria is a typical example um, of countries that are malaria endemic. So, endemic malaria describes the persistence of malaria transmission within a geographical location. This implies that malaria is already established as long-term existing disease in the geographical location. So we are not looking at malaria here as an epidemic, but rather as an endemic. So it's important for us to go through some biological bedrocks, and we have the following. The ecology of mosquito vectors and malaria parasites affect the incidence, seasonal transmission, and geographical range of malaria. And these happen to be the major purpose or the major reason why we are considering the effect of climate variables on the transmission of malaria. Long before now, just like Prof told us yesterday, the issue of climate change have been a discussion. And recently, especially after the COVID-19 pandemic, world leaders have been trying to look at what climate change may actually impact on public health. And part of the diseases that have been major concern due to rising temperature, aside the fact of maybe having floods and also and other hazards, the issue of rising temperature has brought a lot of concern and making people to ask the question of what is going to happen in the midst of this. We have some diseases that are vector-borne diseases, like the case of malaria, whose life cycle is dependent on temperature, and there is the question of as temperature continue to rise, what is going to be the effect of these on some of these vector-borne diseases? Are we going to have a shift, or are we going to have expansion of geographical range? All right. So now um, we know what ecology is. It's just a relationship between the living organism and their environments. So knowing that the vector of malaria is actually the mosquito, one of the things we want to look at is how the habitat or we want to also look at the ecological part of the mosquito, because there are factors that also affect the survivor of the mosquitoes, and this is very, very important in incorporating maybe or in explaining the dynamics of the mosquito population. Very, very important. I cannot overemphasize what Prof has been telling us since the school began, the importance of understanding the biology of the disease. Now, in this case, the disease we are looking at is not just it's not just the human part alone. We have it's a kind of heterogeneous population in that we have the mosquito population and we also have the human population. So it's very, very important to understand the part of the human and also the part of the mosquitoes. Please, are we together? All right. So now, there are abiotic factors that influence the survival of mosquitoes in their natural habitat. And some of these abiotic factors are climate variables. We have other factors, but the one of interest based on the course we are looking at now are the um, climate variables. These climate variables are temperature, precipitation, which include rainfall and snowfall, wind, aridity, and the likes. Okay, so rainfall. How does rainfall affect the mosquitoes? One, it creates mosquito breeding sites. Then two, um, the rainfall also leads to their mortality. And as somebody who want to incorporate rainfall into your model, one of the things you want to ask yourself is what aspect of the dynamics of mosquito in the transmission of malaria, what aspect of it, all right, um, is explainable by rainfall? So are the questions you want to ask. For instance, now, we are just looking at malaria as a typical example. You may have some other diseases that are influenced by climate variables. So now you have the question of how do I put this into my model? I need to submit to you again that one thing very, very important for you is having understood the transmission dynamics of the disease. Uh, there are parameters that have been integrated to explain the dynamics, isn't it? So you also want to understand what parts of these parameters or what classes of these parameters can be explained with the aid of these climatic variables. That is, which of them are dependent on these climatic variables. Are we together? Are we together? All right. So even though rainfall creates mosquito breeding sites, high rainfall also can flush their habitats, leading to the death of the immature mosquitoes. So too little reduces the habitat, too much can flush out larvae, and then moderate one can sustain their population. Then we have the humidity. High relative humidity increases mosquito survival and activity. In fact, when mosquito, we are trying to look at their habitats and also how they are able to interact, how they are able to function in their habitat also, or the environment where they have found themselves. And all of this has to do with also their daily behavior also. So the humidity, when the humidity level is suitable for them, it may cause mosquito to want to bite more. Are we together? So then we have wind and vegetation. Wind affects mosquito dispersal. Vegetation offers shade and breeding protection. Then for the temperature is an important driver of malaria risk since it influences the Anopheles mosquito and Plasmodium parasite growth and survival rate, as well as the biting rate of mosquitoes. These are key things that we need to note. Very important. I'm going to take that of the temperature again because this particular lecture, I may not be able to look at everything, but one thing is that if you are able to understand one of the things I'm going to introduce us to today, then we can build on it to work on the other ones. All right? Okay, so we have one. It influences both the Anopheles mosquito And the Anopheles mosquito has to, that begins rightly from the egg parts, okay, to the larva, to the pupa, and to the adults. And also the Plasmodium parasite growth, which is the pathogen, in this case, Plasmodium falciparum. So now, the development of the Plasmodium falciparum within the um, female Anopheles mosquito is dependent on temperature, what we call the extrinsic incubation period. The extrinsic incubation period is temperature dependent. There is a level of temperature that makes it to grow faster, making the mosquito to become infectious. And when it bites a susceptible human, then the person can become infected. So, meaning now that when there are favorable temperature that makes the pathogen to develop faster, all right, then the mosquito is able to infect more, at least during their lifetime. Okay, so I would like to go through the thermal responses of biological traits. So let's begin to narrow it down little by little, looking at what are the biological traits that are associated with mosquitoes. Like I have said, it's very, very important for us, very, very important for us to understand the biology of, of the disease that we are going through, because that is what eventually we are integrating into the mathematical model. Biological traits are measurable features or characteristics of an organism that can affect one, its survival, two, the reproduction, or performance. And all these three, they have a lot to do with mosquito, which is the vector for malaria. Biological traits can be structural, physiological, or behavioral. And we have examples. These are just general examples. We are going to look at particular examples that are related to mosquitoes. Examples of biological traits include the metabolic rate, the enzyme activity, the locomotion speed. These traits typically increase with temperature up to an optimum point, then decrease if it gets too hot, giving us a kind of unimodal shape. Now, what do we mean by this? This is very important for us. Now, we have this trait, although we are still going to look at them, but let me just quickly explain what is here. All right. Um, so, so I said this trait typically increase with temperature up to an optimum point, then decrease if it gets too hot. Now, there are temperature values where mosquito can survive, or where some of these living organisms can survive. Yeah? Yes, we are still going to look at that. Don't worry, I will entertain questions later. We are still going to look at that. So now, let's take for instance, let me explain what that one is just, that statement is saying. So, um, take for instance, maybe we have the temperature value beginning from, let's say, 16 degree to 35 degree. No, we are looking at um, their response. So what we have here is actually temperature values from 16 to 35. So there are other temperature values within. And then we have a particular biological trait on the y-axis. Okay? So now, due to their physiological response to, to temperature, at some specific values like this 16 now, the response may be very low. And then as temperature increases, all right, then it also begin to increase. Then there is the optimal temperature where the biological trait is at its peak. That is where it behaves so well, where it's able to move and all of that. So we call that one the optimal temperature. Then immediately after the optimal temperature, what we begin to see is that there's a sharp decline in that trait. And if you look at it very well, this gives us something that look like a unimodal function. When you say a unimodal function, it's just a function that just have just one peak. All right. So this one gives us the behavior of some of the responses that have been observed among living organisms with respect to temperature. It is not only limited to, it is not just limited to mosquitoes alone. There are several organisms who also exhibit similar behavior. All right, so this slide, please. Now let's look at biological trait of female mosquitoes. Biological traits relevant to the dynamics of mosquito population for the transmission of malaria include one, development traits. And now, just like what Prof mentioned this morning, it's very, very important that you understand not just only the aim, you have a direction, you have the peculiar questions you want to answer as far as the disease is concerned. And that will guide you to know the kind of model that you're going to use. But for explanation's sake, I'm just talking broad so as to try as much as possible to be able to cover for several questions that people may want to answer as far as malaria or other diseases are concerned. For instance, for the development rate, it describes how fast mosquitoes goes from egg to larva to pupa to adults. And each of these stages is temperature dependent. Faster development in warm temperature can lead to more mosquito generation in a season, increasing population size. We are still going to dig deeper into some of these to see how this can be explained mathematically. The second one is the survival rate or the mortality. The likelihood a mosquito survive each life stage, this is stage, or day. Higher survival at certain temperatures, the population of mosquitoes that will live long, higher survival at certain temperatures, the temperature of the population of mosquitoes that will live long enough to transmit the disease. Then we have the biting rate, which describes how often a mosquito bites a host, humans in our own case. More bite is equivalent to higher chance of malaria transmission. Temperature often increases biting frequency up to a point. Reason being that, and why that? That is due to the fact that when the mosquito, why mosquito comes to actually bite is to get blood from us humans, and that is due to the fact that the blood contains protein that is the fertilization of the eggs. In the absence of, we have several species of mosquitoes, and not all mosquitoes actually suck blood. But the female Anopheles mosquitoes that is responsible for the transmission of malaria, especially in Nigeria here, Anopheles gambiae, suck blood in order to fertilize the egg. And the fertilization of the egg to mature so that it can be oviposited is temperature dependent. So now, when there are favorable temperature that is the quick fertilization of the egg, right? That means it can always make the mosquito to want to come back again to bite. Why? Because the fertilization of the egg happens within short period of time. Are we together, please? All right. So we have the extrinsic incubation period, the time it takes for the Plasmodium falciparum to develop within the mosquito and become transmissible. Higher temperatures typically shorten the EIP, which is the extrinsic incubation period, which increases the likelihood of transmission since mosquitoes do not live forever. Then we have the adult mosquito lifespan, which is also affected by temperature. This describes how long the female adult mosquito lives. The female adult mosquito must live long enough to incubate and transmit the pathogen. Without that, they can't infect any humans. They can't infect anyone. These processes can be hampered actually by the temperature and also humidity. Then we have the egg deposition rate. This is the rate at which a mosquito lays eggs per gonotrophic cycle or per day. Temperature influences metabolism, digestion of blood meals, and also egg maturation. And at optimal temperatures, female develop eggs faster and lay more eggs per cycle. Delays and low eggs are associated with lower temperatures, meaning at low temperature there's going to be a kind of delay, right? And that is why in some region in the world, mosquito cannot survive because of the temperature. Then we have the vectorial capacity, a composite measure of a mosquito's ability to transmit malaria. It is a trait influenced by multiple number of temperature dependent subtraits, and that depends on the biting rate, the EIP, and also survival. Now, these traits respond, so the traits that we have talked about, these traits respond to temperature, rainfall, and other environmental factors. So that is what we call the thermal response. So now, in modeling, what you want to model and incorporate into your malaria model is the thermal response. The thermal response of the mosquito based on a particular, looking at a particular biological trait. You want to look at the thermal response. For instance, now it may be that at a given temperature, the mosquito is able to lay a particular number of eggs. At a given temperature, the mosquito may die out. Please, are we together? Those are the thermal responses. So these traits are usually modeled to predict changes in disease risk under climate change and or control intervention. Sometimes now on the news, the world leaders, they meet to look at climate change. We have malaria in Nigeria and other countries in Africa. Now, in the midst of climate change, you want to see we have control interventions, we have the climate change. Now, you want to see the complex, or you want to look at the interaction between this non-climatic factor, which is control interventions, and the climate factors, which are the rainfall and the temperature and the other ones that may be of interest. So thermal responses or biological traits associated with female Anopheles mosquitoes have been modeled by several authors using linear functions. Please, let's take notes. Or as linear responses. These are not ecologically realistic models. Now, just like what I explained to us earlier, there are several work that has been done to study thermal responses of living organisms, that is responses of organisms to rising temperature and all of that. And one of the conclusions that have been made is the fact that they exhibit unimodal response, and that looks like this. But there are models that have been developed by several authors, several research scientists that model some of these traits as a linear function or linear response, and linear response looks like something like this. But in the real sense, this is not the case. In fact, as a result of some of these things, there are authors who have made some conclusion that maybe there's a kind of given optimal temperature where transmission is at its peak. But when some of these studies were carried out, it was found out that that actually is not correct. Are we together? All right. So that is why it's very, very important that one understand the ecological part. In fact, if there's one thing our prof, that's Professor Bakari, usually tell us, is the fact that understanding all these things are very important. The ecology of maybe the vector also is very, very important, so that you'll be able to model or capture the behavior of the living organism also. So these are not ecologically realistic models. All right, so now we want to move now to modeling the thermal responses of traits. Modeling the thermal responses of traits. So like I said earlier, several authors I've integrated climate variables, temperature and rainfall into the dynamics of the mosquito population, both immature and immature based on their interest. Some authors are interested in looking at all the stages. Some are just interested in looking at maybe lumping them together, and some are not even interested in lumping them together. They just factor it in the way they want it based on their own research interest. But we'll just look at some of them and then pick it up from there. So this one is just showing the life cycle of the female Anopheles mosquito. So and I also want us to know that when I mention mosquitoes, as far as I'm concerned here, I'm referring to female Anopheles mosquitoes, right? So now, this is a typical example of what I'm trying to say here. Some authors incorporated temperature-dependent mosquito life cycle characteristics. So we want to take a look at an example. So this schematic diagram we are seeing here is just a simple schematic diagram that is just showing us the dynamics of both the immature mosquito and the adult mosquitoes. So I will just try to explain as much as possible. So here we have this one is just talking about the number of eggs that go. This is the egg stage. This is the larva stage. This is the pupa stage. That is the PM. The EM represent the egg stage. The LM larva stage. The PM represent the pupa stage. Then the SA represents the susceptible adult mosquito. The E there represents the pre-infectious adult mosquito, and the IA represents the infectious adult mosquitoes. So what we are seeing here is the progression from the egg to the infectious adult mosquitoes, and how does each of these parts takes place. So each of the sigmas that we are seeing here, the sigma E, the sigma L, and the sigma P, is just talking about the development rates. The development rates from egg, how they develop into larva, from larva, how they develop into pupa, and from pupa, how they develop into the adults susceptible mosquitoes. Then we have the first of infection there, that is the lambda A, that make the adult susceptible to progress to the pre-infectious adult mosquitoes, and also the latent period that made them to also progress to the infectious adult mosquitoes. All right, so like Dr. Afis has taken us through some modeling exercise. So all of this can be presented as a mathematical equation, a system of ordinary differential equations, and that is what we have. That is what we have here. All right, so please let us, it's not something big. Are we together? It's not something big. Everything you are seeing here is coming from what you have here. Remember, Dr. Afis was trying to tell us yesterday, something enters, something goes out, isn't it? So that's the picture you should just have. That's where you should pick it from. Like for instance now, if look at these compartments, for instance, this is the egg, right? So you want to look at what is coming in. This is the only thing coming in, isn't it? But we have two things going out, which is this and this, right? And if you come back to that, you will see one thing coming in, model as logistic growth, and then two things are going up. Sorry, please, this one should be plus. This one should be plus. That was a okay. Sorry, the last minus in the first equation should be plus. Are we there? The last minus in the first equation should be plus. The second also should be plus. The third also should be plus. That was a typographical error, please. In fact, all the last sign, operation sign, should be plus. All the last. Because reason being that actually these two things are going out. Are you getting it now? So if you apply that minus before the bracket, it will be minus minus. Is that? Yes, that's why I said everything should be plus. Or you get the last sign should all be plus. That's a typographical error, please. Sorry for that. So now, so what we have here is just a mathematical representation of what we have in the previous slide. But now, please, let's just pay attention. Please, are we together? All right. So now, so what is the interest here? The interest is, remember when I was talking about the biological traits, the first thing I mentioned is the development rate, isn't it? Now, that development rate is temperature dependent. So if you look at this schematic diagram now, this is development rate. Development of the egg into larva. So meaning now that this guy here now is temperature dependent. So now, one of the things you want to do next, which we are still going to look at later, but let me just give us a priori knowledge, is the fact that actually to come up with this function, you need data to actually come up with these functions. And you need what we call the entomological data. The entomological data that have studied the behavior of mosquitoes, how they develop, at some given temperature, and all of that. And then the next thing you want to do is, since you have the temperature and you have the behavior, the particular behavior of the mosquito, let's say now, the development from the egg to the larva, all right? Maybe the time it takes under some given temperature. Are you getting it now? So now you want to look at that, you want to look at that relationship and come up with a function that represents that relationship. So that is very, very key because since you want to include climate variables, you can't go theoretical. You can't go theoretical. You need entomological data to be able to achieve that. Thank you. All right. So yes. So now, and that goes on for each of the stages. Remember, when I was looking at the biological traits, I mentioned quite a number of things. For instance, now we have the, okay, maybe I should ask this question. So I explained a particular concept that will make the pre-infectious mosquito, that is the EA, to become infectious. And I said that particular trait is temperature dependent. So who can tell me what that trait is? That's the general name. EIP. So I said while I was explaining the biological traits, I mentioned quite a number of things, and I said there's this biological trait that will make the pre-infectious mosquito to become infected. You know, this pre-infectious is already infected. Are you getting it now? All right. So now, what will make it to become infectious? And I said that stuff is temperature dependent. So what is it? Please clap for yourself. Do you know why? It's not correct. Survivor rates. Survivor rates. Thank you very much, but is correctly incorrect. So who want to tell me again? Optimal temperature. Thank you. Incorrect. So now I'm causing something now. And it is that even though you know the answer, you are not sure. Yeah, now let me bail us out. I talked about the EIP, the extrinsic incubation period of the pathogen, which is the parasite development rates, the pathogen development rates. We can't just say development rate. That is general. It's not unique. We're not specific. Are you getting it now? So you can say the parasite development rates. So, and that is temperature dependent. So at specific temperature, when the parasite has developed, then it can progress into this place. So meaning now that this particular rate is temperature dependent. Are we getting it now? So do you now see what Prof was saying? Understanding the biology of the disease. Are we seeing it clearly now? Very important. So I would like to stop here to entertain just 2 questions that we can round up this particular session. Okay, no question for now. Okay. Hold on. Okay, I was just told now that we are not entertaining question at this particular session. Okay, let me just give us a kind of recap of what we have done, because we want to have 10 minutes. Is it exercise or something like that after now? Although my time is not up yet. So all right. So and then when we come back after that, then we'll just finish up with what we have started. But let's quickly roll through again what we have done. Let us not forget, to model the thermal responses is very important for us to understand the biological traits of what we want to model. Very, very important. And the biological traits is due to the fact that we know that the mosquito also responds to environmental conditions in their habitat, which is very, very important. And we have said that modeling these thermal responses as linear function or linear response is actually not biologically correct. It is ecologically not correct. There are studies that have been carried out to verify and to ascertain that. Even some studies even consider they considered about 1,000 plus traits, and they look at about 390 different animals, something like that, to actually establish this particular hypothesis. All right, and we have looked at some of the climate variables that can influence malaria, and we have talked about rainfall, humidity, wind and vegetation, and temperature. So now you can't put all of this into the model. You must have the peculiar questions you want to address, and then come up with how you can integrate this into the model, as I've said. Yeah, we have talked about the endemic, which represents the fact that it is persistence within a particular geographical location. So I think I would like to stop here for now. So when we come back, then I will take it off from here. Thank you.